Two.
I think they can hear you now.
Okay, can you hear us on Zoom? No. No, actually, the audio seems to work.
There you go. Try to quiet.
Okay, hi everybody. Thank you for coming again for the seminar. Today we have a pleasure to have Mrs. Liu from University of Hong Kong, Chinese University of Hong Kong, soon to be Dr. Liu, and Anya made her bachelor in Oxford, then a master thesis in KU Leuven in Belgium, and now she's in Hong Kong doing her PhD. And she will talk about lensing, gravitational wave lensing, and at the end, a little bit about quasi-normal modes, about black hole oscillations. So thank you, Anya.
Okay, thank you very much. I hope everyone can hear me. Yeah, okay. So as Marek said, I'm a PhD student at the Chinese University of Hong Kong. So I spent the last 3 years at this beautiful campus on the other side of the world. With the physics department just at the center here, working on gravitational waves. I'm also a member of the LIGO-Virgo-KAGRA collaboration, so I'm actively working on the current detections and new data that I will also briefly touch upon. So just to make sure everyone is on the same page, I guess most of you know already well enough what gravitational wave signal is. It's just a ripple of space-time produced by a coalescence of two compact objects, two black holes or neutron stars, orbiting around each other, then merging and producing one remnant black hole. And what is special about those signals is they provide us unique information about the strong and highly dynamical regime of gravity. And currently, we have around 100 detections published so far. The majority of them coming from black holes, the blue ones. There are a few neutron stars, but there's much more expected to come. As I mentioned, there's currently an observing run going on, and we expect this number of detections to triple within the next year and a half, or within the 2 years. So what gravitational waves can tell us is they allow us to answer a lot of open questions which were inaccessible before within astrophysics, fundamental physics, or cosmology, such as binary black hole populations, their properties, their formation channels, or gravitational waves also provide a unique probe to test gravity. And they can also tell us more about the distribution of matter in the universe, especially the dark matter. And in my work, I've been mainly focused on those 4 topics: on gravitational wave lensing, systematic biases due to the confusion of different effects in gravitational wave inference, a test of general relativity, and also binary black hole formation channels. And today I'm going to mainly focus on these 3 topics. So all within the framework of Bayesian inference using LIGO-Virgo-KAGRA data. So the first one, gravitational wave lensing, what it really is for gravitational waves, it can be used as a tool to probe the distribution of matter in the universe, especially the matter that we don't see directly, the dark matter. So there has been a lot of probes of dark matter, or a lot of evidence from different scales using observations like the CMB, the bullet cluster, or rotational curves of galaxies, that all points towards the same conclusion, that there is some kind of matter in the universe that we don't see, but we know it exists there because it affects other signals or other objects. So now currently what we know about dark matter is that it's massive and collisionless. We have observed its effect due to gravitational effect on other objects, including lensing. And we know that is a very important ingredient of the whole matter in the universe. It takes around 84%. And we know that it's not a standard model particle. There is no known particle that could satisfy those properties. But there's a lot of things we don't know yet. We don't know what the nature of dark matter, what it really is. Is it a particle? What kind of particle it is? How does it form? And does it interact with any other processes than gravitational? And perhaps gravitational wave lensing could help us answer some of those unknown questions. So what I mean by lensing is really bending of light or bending of gravitational waves. So whenever we have a massive object whenever we have a source emitting light, as it passes near a massive object, the path of the light gets bent. And as an effect, we can observe multiple images, multiple copies of the signal from the source behind. This has been tested, this has been observed multiple times with EM signals, with light, but currently we haven't got any observed gravitational wave lensing. However, we expect this to be very possible to happen within the next few years. What gravitational wave lensing is, it's again, when we have a binary black hole emitting a signal as it passes near a massive object, there may be multiple copies of the signal that get lensed and they get focused such that they arrive at the detector, at the observer. So now, depending on the mass of the lens, we can distinguish different lensing regimes. So here I'm talking about strong lensing and milli-lensing. Whenever the mass is large for strong lensing, we observe multiple signals that are time separated. So the time delays can be from minutes, hours, up to days or months if the mass of the lens is really huge. Let's say it's a galaxy cluster. For milli-lenses, we are talking about much smaller masses. These can be of the order of 100 or 1,000 solar masses. And as an effect, those lens signals are not separated completely. So what we receive is not individual signals, but a superposition or an overlapping signal that's composed of individual lens gravitational waves. And what I've been working on mainly was this second regime of milli-lensing. So currently there has been a lot of effort put into the search of gravitational wave lensing, and most of the studies assume a specific lens mass distribution. Let's say it could be a point mass lens, some kind of spherical distribution of mass, or an isothermal ellipsoid. They call this model also some elliptical symmetry. So what all these models have in common, they assume a specific symmetry, and also they assume the lens is an isolated object. But we know this is not physically correct. We know that astrophysical objects reside in galaxies. They can be affected by gravitational shears, by other objects residing nearby. So on this picture that we have here is only a very idealized picture of what is really happening. And together with our collaborators, we proposed a phenomenological approach. So instead of focusing on those lenses, we just focus on the signal we receive and its properties. So what we did is, for a gravitational wave, we can describe a lensed signal as an unlensed signal multiplied by a function which accounts for all lensing effects. And how does the lensing affect a signal emitted by a binary black hole? There are three properties. There is a magnification in the amplitude, there can be a phase shift, and also a time delay in the arrival time because it travels on a different path. So each of these signals will be characterized by the three parameters, and then we can have multiple signals overlapping on top of each other, forming this kind of superposition that we expect to observe. So we developed this framework and also implemented it using transdimensional sampling, so we can perform parameter estimation with Bayesian analysis. And just to show you the explicit expression here, so what we really did is we modeled this as a sum of individual signals, each of those properties. And I performed the parameter estimation. I simulated a signal that has two component signals. I injected this into the ground-based detectors with O3 sensitivity and tried to estimate all the source, binary black hole source parameters, so the 15 parameters, and the lensing parameters for each of those signals. And here's the result. So I'm just showing an example for the relative magnification and the relative time delay between the two signals, with the orange lines being the injected values and the blue distributions are the simulation results, the posterior distributions. So as you can see, what we recover is in agreement with the injection value within 1 sigma. So within this accuracy, so 1 sigma is the darkest shaded region. Okay, so we know this framework works. Yes, please.
With the amplification factor you have used, it's a regular approximation.
It's, yeah.
For mediating, can we use that? Like, could we use a full wave optics format?
Yeah, so we can use it for a certain mass range of the lenses. It would be around 100 solar masses, the lowest limit. If we go below that, the wave optics effects come into play. They will affect, like, there will be some diffraction effects on the waveform. And for that, in that way, in that case, we can't use this formula anymore. But yeah, this is like for masses from 100 solar masses, let's say to 10 to the 6 solar masses. Yeah. Sorry? Yeah, so this is called the geometric optics approximation. Yeah, yeah. Yeah, and so we've seen this framework works. We can recover those parameters, and then we applied it to real gravitational wave data. So here I'm just showing an example for this gravitational wave signal 200208, for which I run analysis trying to estimate the number of millilens gravitational wave signals, as this is also a free parameter in our analysis. But as you can see, there's not really a very clear peak, or there's no a clear value that is much preferred than the others. Also, from the Bayesian model selection, the base factors, they do not show a very clear preference for a certain value. So in this case, we cannot really say this is for sure millilensed. So in all the analysis we've run with O3 data, there is no event that could be confidently claimed as millilensed, but the search is ongoing. We are currently also running the analysis in the recent data from the last year or so, and perhaps there will be a confirmed event in the near future. So this approach has some advantages. As I mentioned, we do not assume any lens model, so we don't need to know really what's happening there, what object is there. It's more realistic, hence, because we are not isolating ourselves to specific scenarios, and we allow the number of component signals to be arbitrary. What we also did is we can map those properties of the signal we observe to certain lens models to make a selection which one of those would be the most accurate. However, there is a number of limitations as well, as you mentioned. So it's only valid for certain lenses in the certain mass range. So in this case, it's around 100 solar masses and above. As below that, wave optics effects will be important, and we cannot use this simple approximation. We also only assume there is one single lens. There might be more of them, or there may be a whole field of lenses, which we're working on to develop further. And as I said, there is no lens model assumed. So on one hand, it's a good thing, but on the other hand, we don't have a clear picture of what is there. But we can map the properties we get to specific lens models further on as a post-processing. So this is just an introduction of the model, and then I used it to analyze different signals and simulate different signals. And now I'm going to address the challenges we might get from the confusion between different effects that can mimic millilensing. So here I'm showing 3 examples of 3 different signals from different sources and eccentric binary orbits, where the binary doesn't follow a very circular orbit, but there is some kind of eccentricity. There are head-on mergers where we have two black holes colliding into each other. And we have precessing binaries where both of the black holes have a precession spin, and they are orbiting around its plane. So the plane is not constant in time. And all of these signals produce some kind of oscillations within the gravitational waveform that could, in a way, mimic lensing. So in one of the works, what we did is we focused on the precession. So here I'm showing 3 example signals. The first one being unlensed precessing. So there is some spin-induced precession in the signal, but there is no lensing. Then we have millilensed but non-precessing, a millilensed and precessing signal. And as you may notice, all of these 3 cases, so in the top I'm showing this strain evolution over time, and here the spectrograms, they are somewhat morphologically similar. So the question we want to answer is, if we detected one of those signals, can we tell which of these columns it will be fit in? So we performed the parameter estimation and also computed the SNRs of the injected and recovery signals using the BLB Bayesian inference library to answer the question if we can correctly recover the lensing and the precession parameters if we account for either effects or both. And here are some key results. So on the left, I'm showing the recovery of 2 of the lensing parameters, the relative time delay between 2 signals, and the number of signals within the whole length superposition. And the black lines are the injected values. So I know these are the correct values, and the blue and orange, so here they're both overlapping, are the recovery results. So these are at 2 different signal-to-noise ratios. As you can see, we can recover them correctly. We're in agreement with what we injected. And this was in the presence of precession and also when we did not account for precession in the recovery model. So we know that this works well for lensing. But then the problem comes when we want to recover the precession, the spin parameters of the system. So here I'm showing the effective precessing spin, which is a combination of both spins of the system and one of the spin magnitudes of the primary black hole. And the 2 colors now correspond to a non-lensed and a lensed recovery. So what we have in the signal, we know there is lensing and precession, and we try to recover with the 2 models, assuming we know it and we don't know it. As you can see, the orange distributions, they tend to prefer very high values. So these are nearly extremal spins around 0.9 or 1. And so it suggests that when we do not account for lensing in this orange scenario, and the signal tries somehow to compensate for the missing effect and adds on the precession to the signal. So this is a very important message for future analysis that neglecting lensing may affect our recovery of the spin of the binary system, and this might need to be taken into account in the future. Okay, are there any questions? Maybe let me ask before I go to the next part. Yes?
So this analysis of the precession of the spin, do you mean the precession of the orbital plane because of some kind of interaction with the third body, or the precession of the spins?
Of the spins of the black holes themselves? Yeah.
You mentioned it's model independent. So lens model independent.
Sorry, can you?
You mentioned it's lens independent. Different lens models you can recover.
Yeah.
So how is it?
So because in the amplification function we use, we only show the magnification, time delay, those parameters that affect the signal. So you could also rewrite this in the form that is dependent on the lens mass, or like the relative position of the lens and the source. And in that case, you assume a specific lens model. But we only do this.
You only recover the magnification and time delay and phase factor.
Yes, that's right.
So it cannot distinguish models, or can it distinguish
Yeah, so
models?
then we can use this information to map to a specific model. Let's say, yeah, I assume then there's a model that is a singular sphere, isothermal sphere, and I can relate those 3 parameters with the properties of the sphere.
Yeah, okay.
Okay. Yeah.
If you neglect this lensing effect, then the spins of this remaining black hole should be higher than normal.
Yeah, that's right.
And can you already compare it with the data? And can you check whether there is lensing or not?
Yeah, it would be good to, but currently our spin measurements are really poor, like they're not constraining. Usually we like, yeah, what we get in the posterior is not informative at all in the real data. So yeah, for the moment, it's also the noise, like the signal to noise ratios also are not high enough, perhaps. And but I think in the next generation, or like even in the next observing runs, there will be more signals coming in that we hope this should be able to distinguish.
Thank you.
Okay. Okay, then I'll now move on to the next part on testing general relativity with gravitational waves. So just to give a bit of background, because we're switching to a different topic, why should we test gravity at all? So Einstein's theory of general relativity, as we know, is the most accurate theory known. It has passed multiple tests within the solar system with binary pulsars and so on. But all these tests are within the quasi-stationary, quasi-linear weak field regime. And we can say that GR works when the gravitational field is weak. So the mass energy of the system as compared to very dynamical system is not that high. The velocities of the objects we are testing are small compared to the speed of light. And also the gravitational field is rather stationary. But all this is not the case when we are talking about binary black holes or neutron stars that we observe with gravitational waves. And also on the other hand, while we know GR works in the weak field regime, there are a lot of unexplained problems. So we are looking for modified theories of gravity that could slightly modify the GR, but still recover it in the weak field regime, so where we know that is correct theory. It should generally preserve the symmetries that GR has, but we expect it to differ in the strong curvature regime, and one of those regimes are the black holes. So that's the perfect laboratory for us to test. And how do we modify it? There's a number of ways. There's a number of theories. You can add new fields.
Have we lost the connection? I can't hear anything. Can you hear the speaker?
No.
No? So it's not only my problem, yes?
No, it's not only your problem.
Okay. Maybe I will call to Marek.
1, 2, 3. That's
Okay, good.
right. Is the recording on? Or, okay. So I'll just continue then. So what I was saying, like for the spiral portion of the signal, we can model the gravitational wave signal with some kind of frequency-dependent amplitude and phase. And what the detectors are most sensitive, or what we can currently more constrain, is the phasing of the gravitational waves. So one way to consider some theory agnostic deviations from GR is to consider some additional terms to the phase that won't be in agreement with the GR necessarily, but we make sure those terms are small because we only want to modify it up to some small extent. So what I've written down here is the whole formula of the gravitational wave phasing as a function of frequency, for which we can write out specific terms at different Pn orders, at post-Newtonian orders. And then in a very theory agnostic way, we can just add some corrections to this and try to use the signal to constrain those parameters. So this is the spiral corrections to the GR. I'm also going to later talk about the ring down corrections in the later part of the signal. But this is just to give you like a brief intro. Sorry? F, the frequency evolution of the signal. Yeah. So now one of the questions still in terms of the confusing the effects is, could gravitational wave mirror lensing, if we neglect it, be mistaken as false positive deviations from GR? So I together with collaborators, we try to study this using the so-called parameterized post-Einsteinian framework, or the PPE framework, in which we add corrections to the amplitude and the phase where U is a function of frequency. And in our study, as I mentioned, because the current detections are more sensitive to the phasing corrections, we only assume there's this phasing term that's present in addition to the GR waveform. So what I did is I simulated a mirror-lensed signal again. Then I injected it into ground-based detector, assuming we detect such signal, but we don't know there is any lensing present inside it, and performed a testing GR, like a parameter estimation with the Bilby Bayesian inference library. And then I wanted to assess, is there violation of GR? In other words, is this a non-zero value of this correction? So we assumed several scenarios. So just for illustration, I'm showing a no lensing case with a single gravitational wave emitted by a binary black hole. Then we assumed a case which I call large lensing, where there's a very small misalignment between the source and the lens. So there will be a large magnification of the amplitude, and there will be a time delay, small time delay between the two component signals. And also a small lensing scenario where the misalignment is larger, so the lensing effect becomes weaker, and the time delay also increases. So we simulated signals with different black hole masses to see how does the bias depend on the binary black hole masses. In other words, that if the masses are smaller, the signal will be longer. So also how does it affect the signal duration? So different lensing effect strength, as I've shown in the previous slide. So this is just the misalignment of the source and the lens. We tried the recovery of different post-Newtonian orders, and also at different signal-to-noise ratios from the ground-based detectors. And here's one of the results we have. So here's the recovery of chirp mass, which is the parameter that's describing the mass of the system. with two lensing scenarios shown in blue and orange for the two masses of the system, the large and the smaller mass. And again, the black line is the injection value, the value we know is correct. As you can see here, while on the left, the two distributions kind of agree, they can recover the injection value. On the right, there is a larger bias, especially for this orange distribution, which shows almost no support for this correct injection value. So we can see that this is in agreement with what I said, that the smaller the masses, the signal is longer, so the lensing effect can build up, and the biases will become stronger for longer duration signals or a smaller mass system. So this is one of the findings we have from out of the questions I listed. I'm not going to cover all of them, but just to show you the main conclusions we found. So here's the base factor that shows the preference for the PP non-GR model versus the GR model, and the recovery at different PN orders shown as different colors and a different source position. So the lensing effect increases from left to right. And in the largest lensing case, especially at the 2 PN order, we can see there is some weak preference for the PPE model, but still this value is around 5. It's even below 5. So this base factor is not sufficient to confidently claim there's a deviation of GR. We also computed the signal to noise ratios that we get from the recovered signal with this model, and they suggested also that there's a lot of loss of the signal strength. So the recovery model is not a good fit for this signal. So the conclusion is we don't need to worry about this case for the current signals. This is also SNRs of 30, which is the signal to noise ratios we are detecting currently, but this would not be a large problem for the current observations. Okay, so then going to the testing GR with black hole ring down, which is a separate topic here. So the ring down is the last portion of the signal where a newly formed black hole, after the merger of the initial black hole, is very highly perturbed, and it needs some time to stabilize, during which it oscillates. And you can literally think of it as a ring ringing with some characteristic frequencies that we call quasi-normal modes in this case. And this ring down portion of the waveform can be modeled as a superposition of damped sinusoids with some kind of amplitude and sinusoidal shape with an exponential damping here that has characteristic frequencies, the oscillation frequency, omega, and then some damping time, tau. So these elements are just the spheroidal nodes. So for 2 to 0, 2 to 0 is the loudest fundamental mode that is expected by GR to be the longest and the easiest to detect. And extracting the value for the omega and tau for this 2 to 0 mode, we can make estimates of the mass and spin of the final newly formed black hole. Then if we could observe other modes, which are generally weaker, we could use the ring down to test general relativity. How do we perform such tests? One of them is the no-hair theorem. So in general relativity, black holes are Kerr black holes, and they are completely described by their mass and spin. So these two quantities are just functions of mass and spin. However, if we have some deviations, this might not be the case. There may be some kind of black hole hair additional charge that won't satisfy this. So in the most generic way, we can add some deviation parameters to those and try to constrain those with gravitational wave data. And then we test whether the black hole is a Kerr black hole as expected by GR. So we call this whole area of study black hole spectroscopy, but what we really do is we take the gravitational wave data, the later part of the signal, we extract the quasi-normal mode frequencies for different modes, and then we estimate the black hole mass and spin. And what has been done so far is, so here I'm showing the constraint from all the events from O3 catalog, and the blue one is the second catalog, that show the deviation in the frequency, in the oscillation frequency. And GR is the zero value at the right at the center. So we can see that this agrees what our current constraints are fully supporting the GR value. Similarly, on the right, I'm showing the deviation of the frequency and damping time in this two-dimensional corner plot, where the GR value is right at the center. So it also agrees. So detections also support the GR. So currently, and this is all we know, we haven't found any deviations from GR. But what is important for the ring down portion analysis is the signal to noise ratios are generally much weaker, much lower than the in spiral portion of the gravitational wave. So we really need higher SNR signals to be able to extract those additional modes and put better constraints on the deviations. So just to finalize, we are currently at the stage of the O4 observing run, which is here. So we have the 3 catalogs from previous observations from LIGO, Virgo, and KAGRA. There is more coming in. There will be another run of O5 planned in the next few years, which will reach even higher redshifts. So the detection horizon will be larger, and we expect the SNRs to be also higher. And there are also next generation detectors, 3G and next generation detectors planned, including Einstein Telescope, Cosmic Explorer, or LISA that will be in the space. So all this will open up a new window for new sources, new signals, and more exciting physics will be available soon. So just to summarize, I've touched upon a few different topics. So firstly, I've explained that gravitational waves can be used to probe dark matter using gravitational wave lensing. But currently, we have no confident lens detections found. There's ongoing research in the current observations. There are predictions saying that there should be at least one lens signal, strongly lens signal by O5. Also, gravitational waves provide us a unique laboratory to test general relativity with the whole portion of the signal of the spiral, the ring down. They provide us different tests. Currently, we don't have any evidence for violation of gravity, but there's a lot of new observations coming in, and they will open up a new window for sources that were inaccessible so far. So there's a lot still to explore and to study. And thank you very much.
Thank you. Thank you for a very nice talk. I have a question regarding one additional effect you might have in lensing, especially when the lens is moving. You may also have the frequency effect on each of these. Yes, the typical Doppler effects on each of these images. Is it possible to measure that in this situation, or do you have to worry about that?
So in this case, we're talking about very short signals. So they're a few seconds long, and we expect the effect to be very weak. There has been studies in this area, but there might be like longer signals, continuous signals, or like in the case of we have a binary orbiting around
I think that we are disconnected again. Okay, I see that there is no way to ask a question. So anyway, goodbye and have a good day and Merry Christmas and Happy New Year.